Hello, it's lesson 3. If you made it this far, well done. Make sure that you've looked at lessons 2 and 1, and today we are going to be using trig identities, including we're going to be doing some proof, which is a bit fancy. So let's get cracking. First up, here's your proof. So we're going to be proving that 1 plus tan squared x is identical to sec squared x. This is called an identity. You can see that because of the type of equality that's in there. These are really important. You should make sure that you got these pretty visible for you throughout today's lesson. I would suggest writing them on like a scrap piece of paper or something like that and just having them in front of you. I know I have, because I'm going to need them. Now, to prove these, you actually base it in sine squared x plus cos squared x equals 1. And each of them will involve, one of them will be dividing through by sine squared x, and the other one will be dividing through by cos squared x. So let's see what happens. If I divide sine squared x by sine squared x, I end up with 1. If I divide cos squared x by sine squared x, cos on top will be plus cot squared x. So actually this one's b, isn't it? It's that one. Equals 1 over sine squared x. Well, 1 over sine squared x. 1 over sine squared x will be the same as third letter rule, cosec. Cosec squared x. And so we've got the second one. Brilliant. Obviously, if you're in an exam or something like that, all you do is just put over sine squared x, over sine squared x, and over sine squared x, and get to that pretty quickly. Next, you've got dividing by cos squared x. Well, sine squared x divided by cos squared x, well, that's going to be tan squared x. Cos squared x divided by cos squared x is going to be plus 1, is equal to 1 over cos squared x. Well, that's sec, isn't it? Okay, so that's going to be sec squared x. And so therefore 1 plus tan squared x is equal to sec squared x. There it is. That one is the first one. These are important. Make sure that you've got them written down. You're going to be using them quite a bit. They are important. So, first up, given that tan of A is equal to negative 5/12 and the angle A is obtuse. Now, that seems like it shouldn't really matter, but it does, because when you're obtuse, which of these quadrants are you in? Well, that's acute stuff, isn't it? That's 0 to 90 degrees, if you're in degrees. That there is the obtuse one, C, A, S, and T. So it's no wonder that tan of whatever this thing is gives us a negative. It's no wonder because it's supposed to, because it's in the obtuse area. But this one here, the sine one, that should be positive because you're in the obtuse quadrant, not acute, obtuse. Sometimes you get questions like this where it's like between 180 and 270, which is like that. And every so often you'll get a question where it says that it's reflex. Now, if this one would have said that angle A is reflex, because tan of A is negative, I know it can't be in there. So it'll kind of imply it really weirdly, and so I'll know that it'll be in that quadrant, and so therefore, you know, I can do whatever I want from there. Cos will be positive. Just watch out for those ones where it's reflex. It's not always so obvious, but you have to use the sign that's there. It's pretty weird, but it's cool. And sec is to do with cos, isn't it? Remember, the signs of these always go the exact same way, but cos, if we're obtuse, is going to be there, and so that will be negative. So I know that's going to be negative. All right, well, let's get cracking. So we've got tan of A is going to equal negative 5/12. Well, tan of A is equal to negative 5/12. We just created a formula here. We had 1 plus tan squared A is going to equal sec squared A. So I'm actually going to use this one pretty heavily for this one. Okay, so we've got, well, 1 plus tan squared A is going to be negative 5/12 squared is going to equal sec squared A. That's going to be 1 plus 25 over 144, which is going to be 169 over 144 is equal to sec squared A. Now what that means is that sec of A is going to equal plus or minus 13 over 12. But which one is it? Which one is it? Well, we know that sec is to do with cos. If we're in the obtuse, cos is going to be negative. And so therefore we know that sec of A has got to be negative 13 over 12. Just be careful with that. You've always got to consider the signs here. This is big boy maths. Now, on question B, we've got sine of A. Now, sine of A is not too much more difficult, but you can do a little bit of messing around with this. You can do some pretty cool stuff. So what I'm going to do with this is, it's not overly complicated, but I know that this here is sec of A, and so actually I know some other stuff. I know that cos, for example, would be 12 over 13, and I can use that if I really wanted to, which is pretty cool. To actually answer this, there's a few different ways to do it. You don't need to worry too much about how it is that you go about it. Like don't overly stress it. But the first thing is that I would suggest doing that tan of A is actually equal to sine of A over cos of A, which is equal to negative 5 over 12. This is the one that you probably wouldn't necessarily thought of. You can brute force it in loads of different ways. You'll have spotted as well, this is the Pythagorean triple, 5, 12 and 13 are involved. And so I'm pretty sure that I'm going to get 5 over 13 somewhere. But with this, I've got that there. Now, I know that sec is the same as cos A. Okay, 1 over cos A. So I actually know that sine of A multiplied by 1 over cos A is what I've got, is equal to negative 5 over 12. Well, that means that, well, that's sec A, isn't it? So I've got negative 13/12 of sine A is going to equal negative 5/13, 5/12, sorry. Cancel off these denominators. Move everything under, and I'll get sine A is going to equal 5 over 13, which is positive, as expected. Job done. Okay, pretty cool, nice way of doing it. There's lots of different ways to do it, but that's the way that I would have gone around it. It's up to you, but really often we tend to try to get things to be sine and cos if possible. Now, next up, we've got to prove these identities. Now, when you're proving these identities, you must never be going left and right and left and right and left and right and trying to kind of make them meet in the middle. You've got to go left-hand side to make the right-hand side, or you've got to go right-hand side to make the left-hand side. You must never try to go kind of one side onto the other, and the other side onto the one, and try to kind of meet in the middle. It's not a legitimate proof if you do that. So, first off, with question A. Well, I'm going to go left-hand sided because I feel like I've got a bit more wiggle room with these because they've got powers and stuff like that. I think that's quite nice. Also, I don't have an identity for 1 plus cos squared theta. I do have one for that. I know 1 minus cos squared theta would equal sine squared theta. I know that, but it doesn't really do too much for me, to be honest. So I'm going to use a difference of 2 squares here, which is pretty cool. So I'm going to get cosec squared theta plus cot squared theta is going to be multiplied by cosec squared theta minus cot squared theta. Okay. Now, there's no real wriggle room here just yet, to be honest, so I can't really do too much with that. But this I can do some stuff with. I can mess around with that. You could, if you wanted to, try to turn this into cos squared theta over sine squared theta, and this would be 1 over sine squared theta, so you'd end up with a bit of messing around, and you could find out pretty quickly that it comes out as 1. And so I'll show you what that actually looks like. It's pretty cool. So with this, we've got 1 over sine squared theta minus cos squared theta over sine squared theta. And what that'll be is 1 minus cos squared theta over sine squared theta. And 1 minus cos squared theta, you should know from year 1, sine squared plus cos squared equals 1, and so therefore 1 minus cos squared theta should equal sine squared theta. So you get sine squared theta over sine squared theta, which is equal to 1. Okay, and so that whole bracket there turns into a 1, which is pretty nice. In the left bracket, you've got 1 over cosec, which is going to be 1 over sine squared theta. You've got cosec of squared of theta, and so that's going to be 1 over sine squared theta plus cos on top. So I'm going to get cos squared theta over sine squared theta. Okay. Now that's going to be 1 plus cos squared theta over sine squared theta. The denominators are the same, so you can just add those ones up. Now that's produced the numerator that I was after. That's done, but the denominator's not quite there just yet. But you should know again from year one, look, sine squared is going to equal 1 minus cos squared of x. And so therefore this thing will be 1 plus cos squared theta over 1 minus cos squared theta. And it's done. Okay, there's a few different ways to go around this, but that's the way that I would have gone around it. I think it's quite a nice one. For B, well, I can't really see how I'm going to do something with this and then produce this kind of factorized thing. I think it's just a bit weird, and so I'm gonna try to sort of mess around with whatever I can. But I'm going to know that at some point I'm going to probably make mistakes with this. Obviously, I've done it ahead of time to make sure that I'm not looking like a wally on these videos, but you're supposed to make mistakes with this stuff. Don't expect it all to go perfectly. Now I'm going to go right hand sided and try to prove the right hand side to the left. You can do it the other way if you want. You can try to like do a difference to two squares or something mad like that on this, but I'm not going to, because I don't think it'll work very well. But bear in mind, you are supposed to make mistakes with this. So we've got this thing and sec squared theta. So that's just the expansion of the single bracket on the right hand side. That seems okay. Look at what it's got here. It's got coses. You see, look, it's got sec and it's got cos. Now I'm happy enough the fact that I've got sec there. That's fine. But you see this here, I could just turn that into a cos. Keep an eye on what it is that you're trying to turn into, whatever it is. You see here, look, where I had that sine squared and I turned it into cos squared. That wasn't too complicated. But with this, if you look, to even get started on this, I should be looking at the fact that the sine there, I can treat that as something different. Okay? And sine squared theta is the same as sine squared is equal to 1 minus cos squared. Okay, so what I've actually got is 1 minus cos squared theta plus 1 minus cos squared theta, lots of sec squared theta, 1 over cos squared theta. Don't know whether I'm going to need that just yet, but I think I will do, because these two things cancel out. So let's see what happens. We've got 1 minus cos squared theta plus 1 over cos squared theta minus, well, these two things will cancel out, so that'll be minus 1. 1 minus 1, big question, is 0. And so I'm going to end up with negative cos squared theta plus 1 over cos squared theta, which is actually sec squared theta minus cos squared theta. Obviously what I've done is just swap the order there to make it just look a little bit more like that left hand side. If you don't swap the order, it'll be absolutely fine. But make sure that before you start these questions, have a look. You know, if you're looking to try to get cos, then and you've got sine, then it's pretty easy to get sine to turn into cos and cos to turn into sine, and it will generally kind of get you most of the way there. Next, we've got solve the equation for cosec squared theta minus 9 equals cot theta, and it's in an interval. Now, the standard thing that you might be doing, is you might have a look at this and you might go, "Hey, I'm super clever. Look at this. There's a difference of 2 squares there." You shouldn't ever do anything with quadratics until they equal 0, and so there's no reason to use a difference of 2 square, even if you've got something quite complicated looking like this. If it doesn't equal 0, really, it's often just going to be a stupid idea. So don't try and give this as 2 cosec theta minus 3 and 2 cosec theta plus 3 equals cot theta, because it's going to lead you absolutely nowhere. Make sure that whenever you do a quadratic skill, you've got equals 0. Is more than often going to kind of steer you in the right direction. So if we're going to be trying to treat it as a quadratic, we need to get everything to be kind of in the same trig ratio, so either sine, cos, tan, cosec, sec, or cot. So the first thing I'm going to do is I'm going to say, well, I've got cosec and I've got cot. You'll find really often that these trig ratios that don't have a power They tend to be really difficult to deal. They tend to be really difficult to deal with. You don't end up doing very much with those. But the ones that do have powers tend to be pretty nice. So I've got 4. Well, cosec squared theta is equal to 1 plus cot squared theta, and you can see that kind of unlocks things because it matches the cot cot theta there. And so I'm going to get 4 plus 4 cot squared theta minus 9 is equal to cot theta. And so I'm going to get 4 cot squared theta minus cot theta minus 5 is equal to 0. Okay, now factorising that's not overly complicated. I need 2 numbers that multiply to make negative 20 and add to make negative 1, and so that's going to be 4 cot squared theta minus 5 cot theta plus 4 cot theta minus 5 equals 0. And so I'm going to end up with cot theta, lots of 4 cot theta minus 5 plus 1, lots of 4 cot theta minus 5 equals 0. So my factorised version is going to end up being cot theta, lots of 4 cot theta minus 5 equals 0. So there's going to be 2 solution sets. One solution set is going to be when cot theta plus 1, pardon me, cot theta plus 1 equals 0. So solution set 1 is going to be when cot theta plus 1 equals 0. So when does cot theta equal negative 1? Well, cot theta equals negative 1. Well, if that's 1 over tan theta, well, cot theta equals negative 1, and whenever tan theta equals negative 1, you can mess around with that and figure that one out yourselves. You shouldn't be finding that very difficult. Now, tan of theta equal to negative 1, you've got tan to the negative 1 of negative 1. Happens at negative 45. So at negative 45 is one of them. That there, I've just used a calculator to find that out. So I've got there is negative 45, negative 45. Okay. But here this is a little bit strange, because what's going to happen here is you're going to have to kind of use a primary value that's negative, which is quite annoying really. So you get tan theta equals negative 1, and so therefore you've got theta being all the way around here, which is going to be 315. Okay, so theta equals 315 degrees. And then from there you've also got the other one. Now watch out for that as well also, by the way, because you've got C, A, S and T. There's another position here, which is that one there, which is 45, and so in this case you're going to get 315, which is the all the way around one. Sorry, I should have spotted that one. That would be 135, which is 45 less than 180. Okay, so those are the values found by the very first of the brackets, that one. The other bracket, you've got 4 cot theta minus 5 equals 0, and so therefore cot theta is equal to 5 quarters, which is fine. That's okay. It's allowed to be, isn't it? And so that's 1 over tan theta that's equal to 5 quarters, which means that tan theta must equal 4/5. Again, that's absolutely fine. And so we can use tan to the negative 1 of 4/5. So we've got shift tan to the negative 1 of 0.8, which comes out as 38.66 degrees. Cast again, C, A, S and T. So there's 38.66, sorry, 38.66, and so it'll be in there as well. Okay, 38.66 plus 180 will be 218.66, okay, degrees. So all of the values for theta will be 38.66, 218.66, 315 degrees, degrees and 135 degrees. Okay, job done. Now your tasks for this lesson are as follows. I want you to do exercise 6D, questions 4, 6 and 8. It doesn't seem like much, but on questions 4 and 6, you've got quite a lot of like simplification stuff to do. Question 4 is obviously just a little bit easier because it's just a Pythagoras looking thing, but 6 has got quite a lot of stuff and 8 has got quite a lot of stuff. If you want to do some extra bits and pieces, you can, and if you want to go back to the previous exercises, you can, and obviously this shouldn't form all of the maths that you ever do. You should be doing other bits and pieces. With a bit of luck, unless Boris tells us otherwise, I should see you on Monday, Monday the 11th, but these are the things that I want you to have done. You will be tested on this when you're back, so good luck. Hopefully, I'll see you soon.